Hey guys, welcome back to part 3 of the video series dedicated towards friction. In this one we're going to look at a further example that builds on the previous two videos in this regard. Here we have an athlete pushing a sled, and the question then becomes, under what condition does the force that the athlete has to apply become minimal? So should the force that the athlete applies to the sled be directed purely horizontally, and that's something that we've looked at in previous videos, or what happens if I apply it at an angle relative to the horizontal, right? So let's say I was applying it at some angle theta, or if I was applying it downwards at some angle, right? Scenario number 3. So instead of applying it upwards, perhaps downwards becomes better. So under which of these three conditions would the forces that the athlete has to apply be minimal? Upwards, or downwards, or horizontal? Since we've already looked at horizontal, I'm not going to be covering that right now, so I'll be looking at scenarios 2 and 3 over here to unpack that a little bit more. Okay, so let's just create a brief free body diagram. So if I just kind of had to redraw this sled in a very basic format. So let's pretend that this is the sled, and I was applying a force at some angle. So this is the force of either the push or the pull, and I was applying it at an angle theta to the horizontal. We're going to plug in some numbers just now. I'm just going to work with the symbols for now. We already know that since force is a vector, I can deconstruct this into vertical and horizontal components. So the vertical component of this force, let me just try and draw it a little bit more accurate. The vertical component of this force is acting upwards, and its magnitude would be described by F sine theta. And there's also a horizontal acting towards the left, which is described by F cosine theta. Okay, so that's just deconstructing this force that I'm applying into vertical and horizontal components. Good. The second thing that I know as well is that since I'm applying a force to the left, that means friction will tend to oppose this motion. So I'm just going to give that a little f, and it'll be kinetic friction, since I'm assuming at this stage that I've applied enough force to overcome the limiting friction, and therefore motion occurs. So it's the kinetic friction that I'm interested in at this point in time. So in essence, there will be a net movement towards the left. So acceleration will occur in the leftward direction. Alright. The other thing that I know is that there's no acceleration vertically, so I have to factor in the vertical forces. So we know that gravity is going to be acting downwards. Right? I'm just going to give that a W to denote the weight force. And I also know that there will be an equal and opposite reaction by the ground on this particular sled, and that's going to be the normal force. Okay, so now in order to understand what's going to be happening to this entire system, in other words the sled, I have to account for all the vertical and all the horizontal motions, and I'll do that separately. So Newton's second law states that F is equal to ma, so the sum of all vertical forces in this case, because there's no acceleration vertically, equals 0. Okay, so now I'm just going to sum all the vertical forces together, but before I do that, I have to ascribe a coordinate system. So in this case, since motion is going to be occurring to the left, I'll say that anything going up and to the left will be given positive values. Therefore, anything to the right and down is given negative values. So we see here there's two upwards forces. I've got N, so the normal force plus F sine theta are positive. The weight force acting downwards is therefore negative, minus the weight force is equal to 0. Therefore N is equal to, if W goes to this side, becomes positive, and if sine theta goes to this side, it becomes negative. So this would be W minus F sine theta. But we know that the weight force of something is equal to mass times gravity, so I'm just going to substitute that in here. So N is equal to mg minus F sine theta. So this is going to become quite important just now, so I'm just going to put a little box around it so that we don't forget it, and I'll label that equation number 1. So this is number 1. We'll need that just now. The second thing I want to do is look at all the horizontal forces, so all the forces in the x direction. Since motion is going to be occurring in the x direction, we said that it's going to be acceleration to the left. We have to account for that. So the sum of the forces in the x direction are going to cause that net acceleration in the x direction. So F is equal to ma. So now I'm just going to have to account for all the horizontal forces. So we said anything going to the left is positive. So that's just going to be F cosine theta. And anything going to the right, well, the only other force here is the force of friction. So that's going to be minus this force of kinetic friction is equal to ma in the x direction. Okay, so like we did before, I'm just going to unpack this force of friction a little bit. So we know, for example, that the force of friction is equal to mu sub k times the normal force, and this normal force is something that I have to unpack because we've already solved what the normal force is. So I'm just going to substitute this mg f sine theta into this equation here. So this becomes mu sub k mg minus f sine theta. Okay, so now I can substitute this into this equation over here. It looks like it's going to be quite a beast and ungainly, but it's going to simplify quite a bit just now, and then we'll make some sense of it. So this is going to become f cosine theta minus this mu sub k mg minus f sine of theta, and all of that's equal to this max. Okay, so now what I'm going to do is I'm just going to multiply these whatever's inside the brackets out. So I'll have f cosine theta minus mu sub k mg, and then I've got a minus mu sub k times a minus f sine theta. That becomes plus mu sub k f sine theta, right? And then all of that, sorry, I don't need the bracket, but all of that is equal to max. Okay, so now to simplify things a little bit further, I need everything with an f on the one side, since I'm trying to calculate how much force it is that I have to apply in this particular scenario, and anything that doesn't have an f goes to the other side. So this becomes f cosine theta plus this over here, mu sub k f sine theta is equal to max, and this minus mu mg becomes a plus mu k mg. Okay, now I can factor out an f over here since both of these have an f in it, so I'll say f cosine theta plus mu sub k sine of theta is equal to, I could factor out an m here, but I'm not going to for now, just so that when we get to the explanation of things it becomes a little bit easier to understand. Max plus mu sub k mg. Alright, so now I can solve for f because I can divide both sides by this, so it means that the force that I have to apply is equal to max plus mu sub k mg, and all of that divided by this cosine theta plus mu sub k sine of theta. Okay, put a box around that. because this is a very important equation that we'll need to kind of make sense of for now. Alright, so this is applying to this particular scenario here. I'm applying a force at some angle, and what does this equation tell us? Well, if you guys remember, when I applied a force purely horizontally, the force, let me just try and put it in a slightly different color, the force that I had to apply in that case was just this top part of the equation here, max plus mu sub k mg, because what that means is, as I'm applying a force to the left, I have to account for the fact that there's a frictional force that requires me to push harder than if there was no friction present. So it's not just F is equal to ma, it's F is equal to ma plus this frictional component over here. Alright, that's just simply the force of friction. Okay, so that's still what I'm seeing here in the same scenario, even though I'm pushing at some angle. So it's good to see that that's still kind of present. But I have this introduced component down here, and what is that telling me? Well, whenever I have a denominator or a number at the bottom of a fraction, the bigger this number becomes, the smaller this force becomes, right? So in essence what that's saying is that, let me change the color here. In essence what that's saying is that force is proportional or inversely proportional to 1 over this cosine theta plus mu sub k sine theta. The larger this number becomes, the smaller the force required by me will become. The cosine of theta is simply the component of the force that I'm directing in the direction of movement. This mu sub k sine of theta is accounting for this component of the force that I'm applying that's actually reducing this normal force. Remember that friction is proportional to the normal force. So the heavier something is, the more friction there will be. The lighter something is, the less friction there will be. And that's exactly what we're seeing here. This component over here is my traditional normal force, this mg, right? So this would account for my normal friction. However, I'm subtracting the component of the force that I'm applying. In essence, what that's doing is it's making this box lighter because I'm partially pushing it up, and therefore it starts reducing the friction that I tend to experience here. Okay, so what you'll also note is that when this angle gets, say for example, larger, in other words, I start redirecting it further up, right? That means that the cosine component becomes smaller and the sine component becomes larger. That means this number here would overall become smaller, and this number over here overall would become larger, right? Either way, this bottom portion will become larger, which means that this top component becomes smaller. Alright, so hopefully that makes some sense. So in essence what it's saying is that the amount of force that I have to apply would decrease, but how much does that, or how does that compare to the force that I apply when it's purely horizontal? Well, we know that the cosine of any angle can never be greater than 1. So the cosine of, for example, 0 degrees, meaning that this angle is purely horizontal, meaning all the forces being directed horizontally, that largest that can be is 1, and the largest that sine could be is if all my forces being directed purely upwards, which would then in case also be 1, and mu, or the coefficient of friction, is always between 0 and 1. So all of this over here can never be bigger than 1, meaning it's going to be less than 1. And if you divide something by a number that's less than 1, this will always be bigger than if you only had this number over here. Okay, so that in summary means that the force that I have to apply by applying a force at an angle is going to be bigger than the force of purely horizontal. And why does that make sense? Well, if I'm directing a force at an angle, that means there's less of this force that's being directed in the direction of movement, which means I have to apply a greater force in order to get that same acceleration. Let's just try and prove that for a second by putting some numbers in. So if I say the mass, as in the first case, is 40 kilograms, if I say that the acceleration that I'm trying to achieve is 2 meters per second squared, and if I say that the coefficient of kinetic friction is equal to 0.2, what we found in our previous example where it was purely horizontal, the force required was equal to 158.48 newtons. So what we're trying to see now is how does this compare to that number. The other thing that I have to account for is the angle, and let's say for example, for simplicity's sake, I'm pulling at an angle of 30 degrees. So if I chuck all of this now into this equation, I will get a force value. So let's just try and calculate what that is. I'm just going to change the color to green so it can stand out. So what's the new force? So let me just box that in green. So the force that I have to apply is equal to 40 times 2 plus 0.2 times 40 times 9.81, and all of that over the cosine of 30 plus 0.2 times the sine of 30. And what you realize is all of that equals 164.05 newtons. So it is indeed bigger than if I had to go purely horizontally. However, the frictional force has decreased. So in the previous example, and I do apologize, I'm running out of space a little bit, the force of kinetic friction in the previous example was simply mu mg, or mu sub k mg, right? Which was 0.2 times 40 times 9.81, which equaled, let me just double check that in the calculator, 0.2 times 40 times 9.81, 196 0.2 times 40 times 9.81, 78.48 newtons. So that's equal to 78.48 newtons. That's how much frictional force there was. How does that compare to the force of friction in this scenario? So if I just plug in numbers over here, that would be 0.2 times 40 times 9.81 minus the force that I applied, which was 164.05, 164.05 times the sine of 30. And what you realize is that that frictional force works out to, I just have to double check, 62.075. 62.075 newtons. So note how this number is indeed smaller than this number down here. Okay, so there is indeed less friction that I experience. So by pushing upwards there is less friction, but because I'm directing more of my force in an upwards direction, there's less force being directed horizontally, requiring more force application overall. Okay, close to say like 6 newtons, give or take. So not much more, but it is more nonetheless. In the next video we'll look at what happens when I direct it at a downwards angle. How does that compare to this 164.05? Alright, last video coming up.